Now coming to the law of mass action. What is it? Law of mass action. Now write down the law. This law was given by Guldberg and Wedge. We can say that WAAGE. If you can't see, once again I'll write it down. WAAGE, Wedge. Guldberg and Wedge, they gave this law and it's called as the law of mass action. Now what is the law? Write down. The rate at which a substance reacts is proportional to its active mass and the rate of a chemical reaction is proportional to the product of the active masses of the reactants, and the rate of a chemical reaction is proportional to the product of the active masses of the reactants. Again I repeat, the rate at which a substance reacts is proportional to its active mass and the rate of a chemical reaction is proportional to the product of the active masses of the reactants. So here what do you mean by active mass here? Active mass means molar concentration. Means when the concentration is expressed in molarity, that is called as active mass. When the concentration is expressed in molarity, that is called as active mass here. Concentration is what? Number of moles by volume, that is weight by molecular weight into volume of the solution in liters. You have read it in chapter 1. We can say that is called as active mass. The meaning of the word active mass means here molar concentration. Mind it. So now what I said again I repeat the law. The rate at which a substance reacts. So let us say a particular reaction is that A gives product. Rate is noted with small letter r. The rate at which a substance reacts is proportional to its active mass. So rate is directly proportional to the active mass. Now always in this particular chapter you will see, in the next chapter also, that is ionic equilibrium, we will be expressing the concentration in terms of square bracket. When we write in terms of square bracket, what we read it as molar concentration of A. Got it? Or simply concentration of A. Concentration means it is molar concentration. That is expressed in molarity, we can say that. Here we will not read R is directly proportional to square bracket A. No. We will be reading R is directly proportional to concentration of A. Even if I say you also, dictate you also, you will be writing within square bracket. When I say concentration of A, don't write in words concentration of A. You may write, but it's better to write square bracket A. Understood? So that is rate at which a substance reacts is proportional to its active mass, molar concentration. Now to remove this proportional sign, we'll take a constant, isn't it? That is called as rate constant. This is known as K. R is equal to K into concentration of A, where K stands for rate constant or velocity constant or specific reaction rate. We can say that. K stands for rate constant or velocity constant or specific reaction rate. We can say that. Clear? Fine. Now here it is. This is the first part of the sentence I said. The rate at which a substance reacts is proportional to its active mass. We got it. Now the rate of a chemical reaction. That is not necessary always. A reaction will have only one mole and only one reactant. It is not necessary. It can have any number of moles and any number of reactants. Let us say we are having a reaction X moles of A reacts with Y moles of B plus Z moles of C to give you a product. Because why I am writing directly product? Because with the product I am not interested. What is the product? I am interested in here only with the reactant. Alright. So in a chemical reaction, the second part of the statement, what is saying? The law. The rate at which a substance reacts is proportional to its active mass, and the rate of a chemical reaction, this is a chemical reaction, the rate of a chemical reaction is directly proportional to the product of its, what you can say, the concentration of its active masses. We can say that. The rate of a chemical reaction is directly proportional to the product of the active masses of the reactants. Got it? Product of the active masses. So R is directly proportional to, that is A into A, how many times? X times. Instead of that I can write e to the power X. Similarly B into B, how many times? Y times, e to the power Y. And C how many times? Z times C to the power Z. So to remove this proportional sign, R is equal to K, concentration of A to the power X, B to the power Y, and C to the power Z. Because you can see X, let us say X is 2 times A. So A into A, instead of writing A into A, I can write A to the power 2. Suppose it Y is 3B. So B is how many times? 3 times B into B into B. Instead of writing B into B into B 3 times, I can write B to the power 3. That's it. What I said. So the rate of a chemical reaction, this is a chemical reaction, is directly proportional to the product. See, product, I have multiplied. The product of the active masses of the reactants. I have multiplied here. So this is your, what you can say, the formula to calculate the rate from the law of mass action. To calculate the rate from the law of mass action, we can say that. This is a formula to calculate the rate from the law of mass action. Fine. In this way, we that is understand it. Now the question here will come that when I have to find the concentration, how will I find the concentration? Right. Now A can be A, B, C, can be any state. It can be solid, it can be liquid, it can be gas. For liquid, we find the concentration. When the substance is liquid, the reactant is liquid, then we find the concentration. What is the formula? Weight by given weight into volume of the solution. Given weight by molecular weight into volume of the solution, that will give you the molarity or the concentration of the solution. Fine. If it is gaseous, we can find the concentration for the gas, but basically we find the partial pressure for the gas, because gas is measured in terms of partial pressure. Listen carefully, all of you. Listen carefully. Alright. So we can find the concentration, no doubt about it. If the concentration is given, why can't we find the concentration? Alright. Otherwise, generally, strictly speaking, we find the partial pressure of a gas. How do we find the partial pressure? Number of moles by total number of moles into the given pressure. I mean, number of moles means what? Number of moles of that reactant by total number of moles of the reactants. Whatever the reactants are there, 3, 4, 2, whatever it is. Total number of moles of the reactants into the given pressure. That will give you the partial pressure of any particular gas we can say that. Okay, liquid understood. We will find the concentration. For gas, if the concentration is given, it's okay. Otherwise, we will find the partial pressure. That also I have said you. We can also find the partial pressure if the gas is ideal by using the formula PV is equal to nRT, where P stands for the partial pressure. P is equal to N by V RT. We can say that. Fine. Now, if it is not liquid, if it is not gas, if the substance is a solid, if the reactant is a solid, then concentration, remember it, is 1 or unity. In case of solid, the concentration will not be given. The concentration is 1 or unity. It is taken to be as. For example, suppose C solid plus O2 gas. So concentration of C solid is 1 or unity. It is. It will never be given in the question. Listen carefully. Why? Why it is 1 or unity? Let us say this is a solid. This is a solid. So this is a reactant which is solid. So in case of solid, the reaction always takes place on the surface of the solid. Only the surface of the solid. So when the reaction takes place at the surface, how much portion of the solid is used? Very, very minute quantities. So when I find the change in concentration, the initial concentration and the final concentration almost remains the same. Because what I said to you, in case of solid, only the upper portion of the solid comes into play. The total solid does not react. It's a surface phenomena. So hence the concentration of the solid remains constant. How it remains constant? That only I am explaining you. That before starting the reaction, there was some concentration of the solid. After the reaction is completed, you find the concentration of solid. You will find hardly the changes, very, very small amount, negligible amount. That means the concentration remains almost constant only. For that reason, we say the concentration is 1 or unity. Because in case of solid, the reaction takes place on the surface of the solid and it's a surface phenomena due to which the change in concentration is very, very negligible. Due to which, that is, we take the concentration as 1 or unity. So in case of liquid, we find the molarity or whatever is being given. In case of gas, also same thing. If the concentration is given, it's well and good. Otherwise, we find the partial pressure. And in case of solid, nothing will be given to you, because in case of solid, the concentration is taken to be as 1 or unity. Remember it. This will be very helpful while doing the numericals. While doing the numericals, it will be very, very helpful. Now, coming to this particular chapter, that is equilibrium chapter. Now, in case of chemical equilibrium, what happens is that the rate of the forward direction is equal to the rate of the backward direction when the reaction attains equilibrium. That is called as a law of chemical equilibrium. You may write it down. that at constant temperature, when a reaction attains equilibrium, the rate of the forward direction is equal to the rate of the backward direction. Alright, you may write it down that at constant temperature, when a reaction attains equilibrium, the rate of the forward reaction is equal to, or the rate of the forward direction, whatever you can say, is equal to the rate of the backward reaction or backward direction, we can say that. That means if I write a particular reaction A plus B, like XA plus YB, reversible sign gives ZC and WD. So in the forward direction, RF means forward, is equal to KF, concentration of A to the power X into B to the power Y. Similarly, for the backward direction, that is KB, concentration of C to the power Z into D to the power W. That's it. In the backward direction. Now, what I said you, when a reaction attains equilibrium, the rate of the forward direction is equal to the rate of the backward direction. RF is equal to RB. So, KF, concentration of A to the power X, B to the power Y is equal to C to the power Z and D to the power W. Now, if I do KF by KB, so concentration of C to the power Z, D to the power W by A to the power X into B to the power Y. So what is KF by KB? KF by KB is known as KC. Alright, KC means what? Equilibrium constant at a particular concentration. Equilibrium constant at a particular concentration, that is KC. So KC is equal to concentration of the product. So C and D are what? The product, you can see, by concentration of the reactant, because A and B are the reactant. Again I repeat, equilibrium constant KC, alright, which is known as equilibrium constant at a given concentration, C means concentration, is equal to the concentration of the product of its concentration of the product by the concentration of the reactant. Alright, in this way we can find it out, the KC. Now, suppose if the reactants are gaseous, alright, if the reactants are gaseous, then what I said you, we don't find the concentration in that case. What we find? We find the partial pressure. In that particular case, we find the partial pressure. So, partial pressure, what we'll do is that is nothing but, same thing it will be, that is RF is equal to KF instead of, let me write, that is KF, instead of concentration I will write partial pressure of A to the power X into partial pressure of B to the power Y. Similarly, RB is equal to KB, partial pressure of C to the power Z into partial pressure of D to the power W. Now, same thing, RF by RB I will do, that is nothing but it will be your RF by RB. RF is equal to RB, sorry, RF is equal to RB, I will do it. So, it will be nothing but KF by KB. So, here KF by KB is nothing but known as KP. Alright, so KP is equal to, same thing, partial pressure of C to the power Z, partial pressure of D to the power W by partial pressure of A to the power X into partial pressure of B to the power Y. So, we got this formula for KC and KP. Alright, when the reactants and the products are gaseous, I have told you, then we generally calculate the partial pressure. We may calculate the concentration, no doubt, if the question is given. But strictly speaking, for gas, we calculate the partial pressure. So, partial pressure, then this is the formula, RF is equal to this, RB is equal to this. When the reaction attains equilibrium, RF is equal to RB, KF, just like the previous one, I have done it, KF into concentration of this, KF into partial pressure of this, and KB into partial pressure of this. Then KF by KB is what? It is nothing but is your KP. So KP is equal to partial pressure of C to the power Z into D to the power W by partial pressure A to the power X into B to the power Y. So in this way, we calculated KP and KC. Got it? Next, we will find what is the relationship between KP and KC. Thank you.